All right. Hello, everyone. Hope you're doing well. Welcome to this workshop series on artificial intelligence. So this workshop comprises three main courses related to the data science field. The first one is Introduction to Machine Learning. Second one, Introduction to Deep Learning. And finally, Introduction to Docker. And of course, today we're going to start with the first one, which is the Machine Learning course. But before we dive into the course, allow me to introduce myself first. So my name is Abdelghafour HALIMI. I have a PhD in image processing and artificial intelligence from the National Political Institute of Toulouse in France. And I was working as a data scientist for worldwide leading companies such as Pierre Fabre and Atos in France. And I have over a decade of experience in the AI field, working for several projects for different fields, like remote sensing, medical imaging, computer vision, with major organizations such as Airbus, CNES, or the European Space Agency, ESA. And I recently joined the Customization Core Lab. So our Core Lab provides a lot of facilities and expertise in various fields. For example, my colleague James is specialized in 3D data visualization, Ronald in AR/VR, and me and Didier in the data science fields. And finally, our manager Sohaib, who is specialized on creating advanced visualization dashboard. So don't hesitate to contact us. I put you here a link for our wiki page where you can find more information, details about the different services that we are providing and how to book all these facilities. You can check also our YouTube channel where you can find the previous training and tutorials provided by me and my colleagues. Okay? All right, let's start from the top. What is machine learning? Machine learning is a very broad field, and it contains many different aspects. You're going to see a lot of definition of it online. But for the sake of this course, we're going to try to keep it as much as possible practical. So in a single sentence, machine learning is using an algorithm or computer program in order to learn some patterns in the data, and then using that algorithm and what it's learned in order to make some prediction on the future on new similar data. Now, machine learning algorithms are also called models. And we're going to use this term a lot later in the Jupyter Notebook examples. But you can ask then how machine learning algorithms differ from a normal algorithm. The answer is the learning aspects. Let's see an example where a normal algorithm could be a set of instructions of how to turn a pile of raw ingredients into your favorite chicken dish. Maybe you're going to start by cutting the vegetables, season the chicken, preheat the oven, etc. And if you follow these steps correctly, you will end up by having your chicken dish. Now, what's important to note here is that the normal algorithm is going to start with an input, which is the ingredient here, and the set of instructions in order to get the output. Machine learning is different. Machine learning is going to start with an input and an ideal output. And they're going to try to figure out the right instructions. Now, think about it. Maybe not going to work for your first try. You're going to put a lot of spices. Cook the chicken for 200 minutes. Second try, same thing. Season the chicken with extra spices. Cook the chicken with 100 minutes. Third try, still not working, but you start getting closer. Now, when it comes to machine learning, this process can take hundreds of tries and iteration. We call this epochs. And at some point, the algorithm is going to converge, and they're going to find the right instructions. Now, I know that I'm missing and skipping a lot of mathematical details behind this, but this is just a simple way to give you an idea about how machine learning works in a nutshell. So keep in mind, machine learning is going to start with an input, ideal output, try to create some relationship between these two and learn some patterns in order to find the right instructions. And maybe the next time that you're going to have some ingredients into your fridge and you don't know what to deal with it, this algorithm can help you by giving you some idea about the dishes that you can make. Okay? Now, what's the difference between data analysis and data science? Data analysis is trying to gain some understanding of the data by doing a lot of comparison between examples, features, visualizations. On the other hand, data science is taking this a step further by doing a lot of experimentation on the data in order to gain some insight within it. One of the experiments that you can do is building a machine learning model So as you can see, data analysis and machine learning are part of the data science field. Now, what you're gonna try to cover today. Again, as I said, we're gonna try to keep it as much as possible practical. We're not gonna enter into the mathematical details. And you're gonna try to see the different steps that you're gonna face in a real machine learning project. And you're gonna try to build a framework that you're gonna use later and adapt it for your own problem. Now here, I try to summarize the most important steps in a real machine learning project. In general, machine learning comes in three main parts: data collection, data modeling, and deployment. Data collection is how you're gonna get the data. Maybe by downloading it from the clouds, servers, doing some web scraping. Deployment is how you're gonna share your model and application. Maybe by creating a dashboard or API. And the most important part, data modeling, and which we'll be focusing on this course. And we're gonna try to go through these different steps: problem definition, data, evaluation, features, modeling, and finally experiments. Let's start with the first one, problem definition. What problem are we trying to resolve? Now, before we get into this and see the different machine learning problems, I want you to know first that machine learning is not the solution to every problem. And it's not always the best choice. And I need you to know first when you shouldn't use machine learning. If a simple hand-coded instruction-based system work, go for it. Forget about machine learning. It's a waste of time. I mean, for the previous examples, if we had already the instructions to get our chicken dish, this is the best model that you can get. Machine learning is going to be a waste of time. Don't do it. Of course, on any other kind of scenarios, machine learning could be very helpful and useful. Now, when you're going to start a new project, you're going to have a business problem. And you're going to need to match it to a machine learning problem, right? These are the main type of machine learning problems. You're going to find supervised learning, unsupervised learning, transfer learning, and finally, reinforcement learning. Supervised learning is when you're going to have the data and the labels. And the machine learning algorithm is going to try to predict this label. And if he gets it wrong, you're going to try again until you find the right label. Now, this act of correction is why it's called supervised learning. Now, supervised learning has two main common inverse problems, either classification one or regression. Classification is when you're going to try to predict if something in one thing or another. Maybe, does this person have a heart disease or not? If it's only two options, we call this binary classification. If it's more than two options, we call this multi-class classification, like predicting dog breeds. On the other hand, regression is when you're going to try to predict a number. For example, how much this house will cost, based on the number of bedrooms, bathrooms, garage, area, location, it depends. Or maybe how many people are going to buy this application based on the advertisements, shares, likes, etc. Now, let's try to run a live demo to illustrate these concepts. Again, I don't promise anything. It's live demo, you know how it goes with this kind of stuff. Let's try to run a live one on my local machine. So let's do this. Let's start the demo. Okay, starting, doing something. Waiting for screen, hide this. Okay, perfect. It's loading. To illustrate this concept, you're going to use what we call the MNIST dataset. It's a dataset of 70,000 images that represent handwriting styles of digit numbers, going from 0 to 9. So as you can see, it's a supervised learning because we have the data, which is the images, and the labels, the digit. As you can see here, let's load some examples. And you can see also that it's a multi-class classification. We have 10 classes that we want to predict. Now, for this example, we're going to give our machine learning algorithm 60K images to train on and 10K to test. And of course, this is how we're going to split the data. We're going to give for each class around 6K for training and 1K to test. And let's run our model on these images and see how is gonna perform. For 5 epochs, you remember? Number of iteration. Now, as you can see, there is a batch here. What does it mean? We have a lot of images. It doesn't fit on my local GPU memory. That's why I'm using a batch, which is just a subset that go through the whole data. This is it. And you can see from this, few epochs, after few epochs, we have an accuracy very high for training, and for validation, same, which is very good. So now the 4th epoch, and we wait until the end. Let's see how we will perform. And again, it's running locally on my machine, doing the training. Okay, let's wait for the final epoch. Perfect, amazing. Don't worry about these graphs. What you need to know is accuracy very high for training and validation. And for the loss function, we need it to be very low for both. Now, he's performing very well, as you can see, 98% for the accuracy, which is amazing. Now, let's try it to load some samples and see how he's gonna perform on data it hasn't seen before. This is the test data. Amazing, he's confident with 100% that it's 9. Okay, let's try another one. 2, perfect. 4, same thing. So you can see that he's very, very good at detecting this. But let's try to make it a little bit harder for the model and try it using my handwriting styles. Let's see how he's gonna perform. Is he gonna be able to predict my handwriting style or not? Let's make 3, for example. Perfect, amazing, it worked. Let's try another one, 6. Here, he got it wrong, which is normal. He wasn't trained on my handwriting styles. Let's try 7, for example. 3, same thing, as you can see. 4, he got it. So you can see that it's not very, very general because I didn't give him a large data set with the whole handwriting styles. This is a small example to illustrate the supervised learning. I gave him the data and the labels, and he was able to train on it and to predict on new data. Perfect. Let's move on to the next one. Let's stop the demo. Okay, let's get back. Supervised learning. Now, imagine you have the purchase history of all your customers at your store, and the marketing team is asking you to send a promotion for the summer. Now, you know that not everyone is gonna be interested on that, right? So you decide to run a machine learning algorithm on your own data. A clustering one, by the way, who's gonna try to group all the people that purchase similar thing. And you're gonna notice that there are 2 different groups. The first group is people who purchase only on the summer, and the second group, people who purchase only the winter. Now you can target the people who purchase only on the summer for the promotion. What I mean here is that unsupervised learning is when you're gonna have the data and any idea about the labels. And it's the machine learning algorithm who's gonna try to predict this without having any idea about them. Let's see an example. Here, I'm gonna use another data set, which is a very known one, the iris data set, which represents 3 species of flowers. Let me reload this. Okay, perfect. So again, 3 species of flowers. Each species has 50 samples with 4 parameters, which represent the sepal length with the sepal width, and petal length and petal width. And if we do some EDA, exploitative data analysis, we're gonna find that it looks like this. If you look at the distributions of this species, Setosa, versicolor, and virginica. These are the different species. And what you noticed, just by looking to the relationship between these parameters, that one of the species is very easy to separate. You see, it's linearly separable. 2 others are difficult. So you can see it, for example, if we should choose the right parameters like petal width cross petal length, you can see this one is easy. even in 3D, as you can see. It's separable. The two others are very difficult. The idea here is that we know the labels, of course, but we're going to give our machine learning algorithm these samples without any idea about the labels. And we let him guess by himself. For that, you're going to do first a dimension tree reduction using PCA to get the most important features. Instead of working with 4 parameters for each samples, you're going to do a linear transformation, which gets the most principal component here. And you're going to have this, and you're going to try to predict on this 2 component, PCA1, PCA2. This is the final one. And let's run our k-means here. Again, as you can see also, I'm helping him a little bit by giving him a number of clusters. There are other models, of course, that predict also the number of clusters. But here, just to show you, I'm giving him the number of clusters like 3 and tell him to guess. And this is the prediction of k-means. And if you compare it to the real one, because we know the data, we know the labels, you can see that he was able to get this class very good. These 2, it's hard, even for him. And I mean, it makes sense, because even for us as a human, it's difficult to separate these 2 classes. Then this is a small animation to show you how we iterate. We start with a random average of a group, and then step by step, you're going to iterate until he converges to the right groups. This is how k-means works. Start with a random state, try to calculate the mean of the samples, and then allocate each new samples to the smallest distance between the average of the group and allocate it to this group, to this cluster. And here, as you can see, he was able to perform it, and we can evaluate it at the end, of course. It's going to give you a question accuracy here, for example, 85%. And he get it, this one very good, this it was, I think, all the samples. Here, he gets wrong on 13, and here on 8, which makes sense when you look at to these clusters. And again, when I'm showing you this, because when you are working, this is very important, with unsupervised learning, you're going to need an expert in the field with you, who's going to tell you if the algorithm is doing garbage or something meaningful that have significance. You need the expert with you when working on unsupervised learning. So this is just an example to illustrate this. Let's move to another one. Next one. Let me stop this demo. Let's get back to the next one. Transfer learning. Transfer learning is when you're going to use what a model has already learned in one domain to help you on another domain. For example, if you want to predict from this image the dog breeds, you're going to use what another model has already done with like classifying and differentiate different car types, and then use it and adapt it and tune it to your own problem. Now, why is it valuable? Because when you're going to start doing machine learning, you're going to see that it's an expensive task. And each model you're going to train, you're going to do a million of calculations. And these calculations aren't free. Sometimes you need to pay for it. So instead of going from scratch and learning what an image is and the patterns inside this image, you're going to use what has already another model done before and just tune it and adapt it for your own problem. And it's going to save you a lot in money and time. This is why transfer learning is very important. Let's see an example of it. So you remember the previous examples with the MNIST dataset, right? We used how much? 70,000 images. Now we're going to use the most famous one, dogs versus cats. Let's see. Let me run the example. All right. Here, for transfer learning, to illustrate this, you can see that the data that we're going to use only almost 2,000 images. 1K for cat images and 1K for dog images. As you can see, it's almost 900. It's not even 1K. And we're going to use, for training, 836 for test. So you can see that it's only 2,000 images, which is nothing. You can do nothing with that if you want to train your models on this. You need a lot of data. Machine learning, deep learning likes big data. So for here, how I'm going to do and deal with this problem, I'm going to use a model that has been already trained. We call this VGG16 on huge data, ImageNet, millions of images and hundreds of classes. And I'm going to just train it on these 2K images, which is nothing, for only 5 epochs. And let's see how you're going to perform. All right, going to start. Same thing, same methods, batch, because it doesn't fit on my local GPU memory. And you can see here the training. For the training set, already we are 70% accuracy, which is amazing. Only for the first 3 epochs, as you can see, we are at 80% accuracy here. Okay, let's see how we're going to perform at the end. Let's see. Okay. Amazing. Just for 5 epochs. You can see here that we got an accuracy for chain 78 and 89 accuracy just for 5 epochs for 2K images, which is nothing. This is why transfer learning is amazing. You should use it as long as you have any pre-trained model that you know. Here you can upload a new image or just test it. We are at 80% accuracy, as you can see. These are images that he haven't seen before, and he is confident he got this right. It's a dog, cat, as you can see. Same thing here. He got them all right. Let's try other samples. Same, perfect. He got this one wrong with confidence 67. He predicted that it's, as you can see, a cat. But this is why it's valuable. This is why it's very important. All right, let's move to the next one. Later the questions. If you have any questions, you can. I'm going to show you how you can contact my colleague Didier and gonna discuss this after the presentation. Thank you. Thanks. Let's move to the next one, final one, by the way. Let me just stop this. Perfect. Let's go to the final one. Reinforcement learning. Reinforcement learning is when your model gonna do some actions and you're gonna punishing it for doing it bad and rewarding it for doing it good. A good example of this is to teach a machine learning model how to play chess or the game Go. By the way, the most and the best one till now is the one provided by Google DeepMind. It's called AlphaGo. And these kind of problems are very used for robotics and video games. Let's see an example of it. Here, I created a game, a small maze game. Let's see this. And I'm going to try to train an agent by giving him some rewards and punishment. And let's see if he's going to converge and find the right path or not. I don't know. Let's see together this. Let me reload the page. Okay, this is the game. I'm going to give him episodes. How many games he's going to play. Let's put it 100. And let's train our agent. Here, you're going to see that I'm giving him some rewards and punishment. And you can see the trend. It's improving. And the number of episodes here, as you can see. And each time, I'm changing the parameters in order to make him try to converge and find the right path. And as you can see, let's see if you're going to converge or not. Amazing, he converged, he find the right path. And you can see the different simulation here, how he was trying to learn, as you can see, all the different episodes, so the games, with the last rewards, negative and positive each time. And at some point, you're gonna see that he converged and he find the right path always, as you can see here. Amazing. This is perfect. But just to give you an idea, let's reset this. This is how he's working. When I move in the right path, I'm giving him 1+1, as you can see. If it's in the wrong way, -3, a punishment. And based on this, he was able to find the right path. This is an example of reinforcement learning. Perfect. At least all the demos works, so this is good. Let's move on. Stop this. Get back to the presentation. All right, so now we know how to match our business problem to machine learning problem. Supervised learning, I know my input and outputs. And supervised, I'm not sure of the output, but I have the inputs. And finally, transfer learning, I think my problem may be similar to something else. Let's move to the next steps, data. What kind of data do we have? Now, data comes in many different shapes and size, but the two most common ones are either structured or unstructured. Structured are like CSV files, Excel files, tables, data frame. Unstructured are like images, audio file, email. Now, these kind of data can be either static or streaming. Static means it's not going to change over time. It's going to be static. If you take this medical patient record as CSV file, you can see that it's static and it's not going to change. And the more data do we have, the better. On the other hand, streaming is when your data going to change over time always, like stock market price, time series data of dioxide carbon, for example. And this kind of data is very used to do some monitoring and forecasting. And this is a common data science workflow, as you can see. You have your static data, for example, here, CSV file. You're going to create your environment using Anaconda, for example. Then, in order to make it easy to the language that you are working on, Python, for example, you're going to use a library called Panda to convert this into something the language can understand, a data frame. Then you're going to do some data analysis using Matplotlib and build finally your machine learning model that's going to predict if someone's going to have a heart disease or not. And finally, you can deploy it as an application. As you can see here, this is a heart disease prediction app where someone can upload a CSV file of medical patient records, and then you'll be able to do some data cleaning. For example, removing duplicates, handling missing values, encoding categorical features, doing some scaling. Now you have your data cleaned. You can move to the next step, which is model training. You can choose the model that you want to work with it, maybe random forest, support vector machine, logistic regression, as you wish, and you can play with the different parameters. And then you can train your model. And it's going to give you a score, 90% here, accuracy, amazing. It's going to give you the most important parameters that allows you to get this amazing score here. And then you can make some prediction on new patient. You're going to give him the new parameters, and it's going to give you a probability of heart disease with 76% here. And to give you the most important parameters also, you can play with the different parameters of the new patient and predict using the trained model. Here, it's negative. Probability of heart disease is very low. This is an example how you can build a pipeline and application for your own problem, right? Let's move on. Next one, evaluation. What defines success for us? And what metrics are we going to use to measure the performance of our model? Now, when you're going to start a project, you're going to need to fix a goal first. For this project to be worth pursuing further, we need a machine learning model with over 99% accuracy. So for this example, 97, it's not worth pursuing with this model. You need to change it. Same thing for classifying car insurance. Is it his fault or not? If it's under 95%, you need to change your model. What I mean here is that whenever you start a new project, you need to fix a goal. A reasonable one, not like these examples. 99%, it's a lot. It's not reasonable at all. And these are the different metrics related to the problem that you're working on. For example, for classification, we're going to find accuracy, precision, recall, confusion matrix, classification report. For regression, we're going to find mean absolute error, mean squared error, RMSE, or R2 scores. All right. Next one. Features. What do we already know about the data? Now, features mean different forms of the data. If you take the previous examples of the medical patient records, as you can see, we want to use these parameters, the weight, the sex, heart rate, chest pain, to predict these heart disease. Now, these parameters are called feature variable. And the one that you want to predict, it's called the target variable. Now, these features can be either numerical, like the weight, heart rate, chest pain, or categorical, like sex, male or female, heart disease, yes or no. Now, sometimes you're going to find what we call derived features, which means you are the one who's going to create this based on your own data. Like this one, how many visit last year? Or did he visit last year, yes or no? We call this feature engineering, looking at different features of the data and creating new ones based on your own data. Now, these features, as you can see, are related to structured data. But unstructured data has also features. If you take this couple of images of dogs, we're going to launch machine learning on these images, and you're going to find different shapes, 4 legs, 2 eyes. These are going to be the features that the machine learning are going to use to resolve computer vision problems, for example, object detection, or pattern recognition, for example. All right. Now, what features should you use? Here, try always to use the features that cover all your samples. Again, all your samples. This is the best case. If you look at this feature, most eaten food, it covers only 10%. This is a bad one. It's going to give you a bad model. Don't use it. Try always to use the features that cover all your samples, or at least 80%, and then we're going to see how we're going to handle these missing values. Okay. Next one, modeling. Here I break it down in 4 main parts. So the first one, which is the most important concept in machine learning. Now, when you're going to start doing machine learning, you want your model to perform very well on new data. You need to do this. You need to split your data into training, where you're going to train your model, validation, where you're going to tune it and improve it, and finally, a test where you're going to compare on this. Now, why this is very important? Think of it like this. Imagine you are a student, and you want to learn new subject, new course on AI, by example. You're going to start by doing the course materials, right? This is going to be corresponding to us to training set. Then you want to practice yourself on some practice exam. This is going to be corresponding to us to validation set. And finally, you're going to pass the final exam. This is going to be the test set. Now, if a student learns the subject and gets a good score and a good grade, it means that he learned the subject. He knows what he's doing, right? Now, this act of adaptation in machine learning, it's called generalization. The ability of a machine learning model to perform well on data it hasn't seen before. And this is exactly what you are looking for. We are looking to our model to be as much as possible general. This is very important because imagine there is a leak of the final exam. The professor gives them the final exam. Everyone's going to get a good score, right? But did they really learn something? Probably not. Probably just memorization. And this is exactly what you want to avoid when doing machine learning. We want to avoid our model to be memorizing things. We're going to see that it's called overfitting layer. We want our model to be as much as possible general. This is very important, right? Now, This is a small example how we can do it with 100 patient records. In general, we take for the training 70, 80%, and for the validation test, 10 to 15%. Now, each part of this is going to correspond to us to do something. The training, to choose and train our model. The validation, to tune it and improve it. And finally, the test data to do model comparison. Let's start with the first one, choosing a model. Now here, again, it's not a rule. It's by experience in general. When you are working with structured data, like CSV files, Excel files, data frame, tables, machine learning algorithms tend to be working the best, like CatBoost, XGBoost, like GBM. And when you're working with unstructured data, like images, audio files, deep learning and transfer learning tend to be working the best. Again, it's not a rule. It's by experience. You can use it as a start point. Now that you have chosen your model, next step is to train it, right? If you take the previous examples, here the medical patient records, we're going to use these parameters, which are going to be called X, to predict the labels, Y, this column. Now, what the model going to do when you're going to train, you're going to try to create a relationship between these Y and X in a form of Y equal H of X. H is going to represent the model. And here, each model has its own way of doing it, right? It can be a linear model, non-linear, decision tree. It depends on the problem that you're working on. If we take a small example of regression, problem of regression, you're going to see that our model is going to be equal to theta 0 plus theta 1 x. Theta 0, theta 1 going to be the parameters of our model. And then we're going to fix what we call a cost function. Here, it's the mean squared error between the prediction and the true labels. And the idea behind training a model is to minimize this cost function based on these parameters by updating them using optimization methods like stochastic gradient descent or Adam algorithm. It depends. And this is a small example of it. So in blue, we have the true value, and in red, our model. And the idea is to minimize this error. Again, this is just to give you an idea. We don't care about it. Forget it. Your goal of you is going to be to minimize time between experiments, because when you're going to do machine learning, it's going to take a lot of time training these models. So, 2 tips. First one, never start with the whole data. Big mistake. If you have 100,000 samples, don't use them directly. Use a subset. 10K, for example. Start with this. Second tip, start always with small model and then add some complexity. And it's going to save you a lot. In time, you can try a lot of different models. Now, things to remember. Some models work better than others on different problems. Don't be afraid to try things. Do it. Don't care. Try. Play with your models. As long as you follow the 2 tips that I said. Next, start small and build up and add some complexity as you need, of course. Next one, tune in a model. Now, again, yeah, the question at the end here first. Yeah, at the end. Yeah, thank you. So, again, tune in a model. If you take the previous examples of the chicken dish, as you remember, you can see that cooking a chicken at 4 hours, 300 temperature, 300 degree, is not as good as doing it for 1 hour, 200 degree. This is how you can tune the oven. Machine learning is the same thing. Each model going to have hyperparameters and parameters that you can play, adjust, change, do whatever you want with them until you get a better model. If you take random forest, for example, you can see that the trees is a hyperparameter and parameter of the model. You can play with it, add some complexity. Same for neural networks. The hidden layers are considered as a hyperparameter of a model. You can play with it, add some complexity until you find the better model. All right. Things to remember, machine learning models have hyperparameters that you can adjust. A model first results aren't it last, of course. And tuning can take place on training or validation dataset. Here it depends on the size of the dataset you have. If you have small dataset, you can do also the tuning on the training set also. Okay, next one, model comparison. Here, when you're gonna do all the previous steps, tune your model, choose it, train it, tune it, you wanna test it on new real samples, right? New data. Here you're gonna face two cases. Either your model gonna do very bad on training and very bad on test, or very good on training and very bad on test. And what you are looking for is the third case, where your model is gonna be doing very good on training and test. Now, these two cases are very known under the name of underfitting and overfitting. And this is an example of it, as you can see here. This is the underfitting and overfitting related to regression and classification. As you can see, what you are looking for is the second, this one, optimal fitting. Now, there are many several reasons why this can happen, but the common two ones are either data leakage or data mismatch. Data leakage, if you remember, there is a leak of the final exam for the student. You remember this? This is data leakage. It means that there is a leak between test data and training data. This is why we need to keep at all costs separate the test data from the training data. Now, data mismatch is when you're gonna train on different kind of type of data and test it on another type of the data. This is what it means, data mismatch. Sometimes the underfitting also happens if you don't train your model for a long period. Here I put you some fixes for the overfitting and underfitting. For underfitting, try more advanced model, increase model hyperparameters, you reduce amount of features, train for longer. Overfitting, collect more data, or try less advanced model. Okay, now that you have fixed these two problems, next step is to compare our models. Here, it will depend on the goal that you have set and the problem that you are working on. What I mean here, imagine you are looking only on the model that perform very good, the best performance. You don't care about the time that's gonna take to train it or to do the prediction. Third model is gonna be the best for you, right? Now imagine you are looking for something real time, computer vision problems. The prediction time is very important for you. Training, same thing. The first model is gonna be the best for you. Now imagine you are looking for a compromise between these two. The second model is gonna be the best for you. What I mean here is that it's not always the model with the best performance, the best model. It depends on the problem that you are working on and the goal that you are looking for, all right? Things to remember, want to avoid overfitting and underfitting, keep the test set separate at all costs, compare apple to apple, of course, same kind of type of data, and one best performance metric doesn't equal the best model, as I said. All right, next one, experimentation. Okay, you know all these different steps, okay? What you're gonna notice, it's gonna be an iterative process. What I mean here is that you're gonna start doing it, get a bad model, try again, good model, try again, perfect model. What I mean here is that when you're gonna work really, and you know, even if you know all these steps and start working on machine learning, your own problem, you're gonna face problems that you didn't expect related to your own data. And you are the one who's gonna resolve this by your own, which means you're gonna need to do a lot of experimentation by your own. Experimentation in machine learning has a very high weight. You need to keep it in mind. Experimentation is very important. You need to experiment by yourself. Okay, now we know our framework. In order to build it, we're gonna try to match it to some data science and machine learning tools. For that, you're gonna have your computer, you're gonna build the environment using Anaconda, for example, and then try to match this library to the parts that we have seen. For example, the data science here, it's gonna be matched with Anaconda and Jupyter Notebooks. Then you're gonna have the data analysis, you're gonna use Panda, Matplotlib, NumPy, for example. And for the modeling machine learning, we're gonna use libraries like TensorFlow, PyTorch, Scikit-learn, etc. Today, we'll be focusing on Scikit-learn. Why? Because it's built on Python, has many inbuilt machine learning models, has a lot of methods to evaluate your models, and very well-designed API. Now, this is this scikit-learn workflow that we're going to try to go through today. We're going to start by getting the data ready, which means doing data cleaning and data wrangling. This is very important. People don't know this, but this is very, very important in a machine learning project. Because as I always say, data is the nutrition of AI. If you're going to give your model junk food, it's not going to perform well. So you need very high quality of the data. This is very important. Next, we're going to pick a model that suits our problem. We're going to try to fit it, which means train it and make some prediction, evaluate it, improve it by doing a lot of experimentation, and finally, save and reload it and test it again. Quick side, I did the same workshops in Arabic for the Arabic audience. I'm talking for YouTube. So again, you're gonna find all the different materials that I'm gonna give you in Arabic. Same Jupyter notebooks, same videos. You can find them in Arabic, and you can follow with me in Arabic and do the exact Jupyter notebooks for Arabic. Now, before we finish, let's play a small game. Let's try to run a small game and play it together. Don't be afraid. It's anonymous. You can use a nickname. Don't be afraid. Let's run this. Let's start by doing a small tutorial first to get the mechanic of the game, right? Here, you're gonna need, you can use your phone or laptop as you wish. Just go to kahoot.it and put this PIN number. Again, it's anonymous. Don't worry. Put whatever you want as a nickname. We're going to start by a small tutorial to show you how you play this game. We're going to try to do 3 different questions. So you're going to have true or false, puzzle, or quiz. This is the 3 different questions. Let's wait a little bit. People join. So again, kahoot.it, and put the PIN number. Okay, have 75 people. Let's see. Do you think we can start? Okay? All right. Let's start this. Still people joining? Okay. Looks like everyone joined. All right, let's start. 3 different type of questions: true, false, puzzles, or quiz. Here, 1 + 1 equal. You have some propositions, 2, 5, 80, or 10. Put the color of the true answer. Trust in you. 1 + 1. Don't wanna get wrong answer on this. Come on. We have the time at the left and the answers at the right. Okay, 77% answered. Ah, this is scary. I don't know with this. Let's say it's on YouTube, but the problem is that I'm not diffusing it in YouTube, so it's someone from here. Okay, let's move on. Let's see. Next one. Here, you need to know that there is ranking. The score here is calculated not only on the right answer, but also the one who is fastest. So the rapidity is important. The one who answer very quickly and get the right answer get the highest score. Let's see. We move. So we have Pingu the leading in part here. All right. True or false? 2 by 2 equals 3. True or false? Okay. Let's wait. 10 seconds. 77 answers. All right. Again, same two people or not? What do you think? Let's see. Okay. Final question. Here, the next mechanism of the game is puzzle. You need to reorder. Arrange the numbers from the smallest to the largest. Here, to get the idea, you need to start from the bottom to the top. So change the colors in order to make the right order from 1 to 4. This is trick one. From the bottom to the top. Smallest, yeah, exactly. This is a tricky one. I let you. It's okay. It's okay. I can understand if someone gonna miss it. This is the hardest one, but yeah. You need to start from the bottom for the smallest to the top. Okay, I can understand. It's a tricky one, but you get the idea. You start from the puzzles from the bottom to the top. This is how you can order the steps. Okay, now we can play the true game. Let me remove this and start the real quiz. Now, before we start this, let's make it a little bit more exciting and interesting. Let's add some motivation. Let's add a small cash prize for the winner, right? Now we can have some competition, right? Let's make it a little bit interesting. So let's do this. But I want you to put your real name. That way I can know that it's you, and I will ask you for your email at the end. Didi, where are you? I'm not here? Not allowed to play. I'm not gonna give you the prize. So, no. All right? Okay? Just put your real name, and you're gonna have small cash prize at the end. Okay, same thing. Go to kahoot.it and join the game. Okay. Can we start or just wait? What do you think? We start? Okay, already? Now there is a cash prize at the end, so focus, don't do the as before. So again, you're gonna have 20 questions. And let's see if you are really listening or just, let's start, okay? At the end. Let's start. All right. Let me put myself here. Okay, what is machine learning? An operating system, a type of hardware, programming language, or method to teach computers to learn patterns from the data. Okay, we have some answers, very quick. Ah, perfect. Same two guys. This is good. This is good. Okay, let's move on. Okay, let's see the board. Malaka is top one. Okay, it's moving fast. So you're gonna have your chance. Don't worry. You're gonna see. All right. We have seen this, just to remember you. Now the puzzles are the difficult one. Arrange the following steps in the correct order for typical machine learning projects. Yeah, bottom to the top. We have data collection, model deployment, data model. We have seen this. Okay. "20 seconds for the remaining 5 people still. Okay. Okay, 46, 31. This is a difficult one. Okay, let's move on. Ah, you see? Shinuri is the one, the top one now. Okay, let's see. Quiz. Which of the following is a type of machine learning? Supervised learning, reinforcement learning, supervised, or all of the above? Okay. Still 3 people. 9 seconds. Okay. All of the above. We have seen this with demos, by the way. Okay. Let's see. Ah, still. Okay. Let's see if you're gonna have some comeback or not. What does the term overfitting refer to in machine learning? This is a difficult one. A model that performs well on training, but poorly on new data, that performs well on new data, cannot learn from data, or that is too simple. Okay. Let me put myself there. Okay. I put myself here. Ah, ABG. Ah, ABG didn't put your true name. Okay, let's see. Quiz. What is the purpose of a validation set in machine learning? To test, to tune, to store the model, or to train? You have seen this validation set, not the test set. Okay, to tune the model hyperparameters. It changed. XZ is the new lead-in one. Okay. Again, there is 20 questions, so it's okay. Which library is commonly used for machine learning in Python? NumPy, scikit-learn, matplotlib, or Panda? Okay, scikit-learn. We have seen this at the end. Okay, Wajih, new one. Top, okay. Question 8. What is unsupervised learning? Learning without labeled data, learning from experts, learning with labeled data, or learning with rewards and punishment? All right, 62 people, okay, you got it. Learning without labeled data. Still Wajih, okay. Question 9, what is now supervised learning? Learning with labeled data, with rewards and punishment, without labeled data? Let's see. Perfect, 67, okay. Learning with labeled data. It's becoming harder. Wajih doesn't let you get the first position. Come on, still have some number of questions. Don't worry, 10. What is the main goal of classification algorithm? To predict continuous value, to cluster similar data points, to optimize the reward signal, or to divide data into distinct categories? Five seconds, okay. To divide data into distinct categories. Okay, I can understand it to cluster similar. This is clustering, not classification, but it's tricky one. Okay, change everything. Mohammed is the new one, okay. Told you, it's moving fast, so you have your chance. In machine learning, what is a feature? Input variable used to make prediction, output of the model, error, or algorithm used for training. Okay, 5 seconds. 3, 2, 1. All right, input variable to make prediction. All right, 64, it's good. Still, okay, okay. Let's see, next one, 12. What is the primary objective of regression analysis? To identify clusters in data, to reduce the number, predict a continuous outcome, or classify data into categories. Regression. Ten seconds. 8. Okay. Perfect. To predict a number. 47. Okay. Okay, Mohammed is still there in the top. 13, what is a model in machine learning? A method to pre-process data, a data set using for training, an algorithm that makes prediction or decisions based on the data, or a type of software. Perfect, 69. Okay, this is good. At least you are listening, so it's perfect. Still in the top. Okay, now we are getting at the end. Last questions. We are at 14. Okay, we still have. What is the primary purpose of a test set in machine learning this time? Okay, 10 seconds. Okay, perfect. To evaluate the performance of the trained model. Okay. Maybe you're gonna get some comeback from Amir. Let's see. 15. True or false? Very quick. Overfitting occurs when a model performs well on training and poorly on test. True or false? Okay. Again, okay. Again, true or false? Do it even if it's like randomly. At least put an answer. You don't know. It's 50-50. Okay. Lana is the second. Okay, it's very close. True or false? Again, supervised learning requires labeled data to train. True. 72. Perfect. Okay. Muhammad doesn't let you get the first position. Okay. Let's see for the, I don't know how many questions remain. But you can see that, yeah, still 4 questions. Okay. True or false? Okay, false. 59. Okay. Now we have only 3 questions remaining. Everything is possible. Just be very fast. Even if you don't get the answer, just very fast. Maybe you're gonna get it randomly. Let's see. True or false? Machine learning features are the input variable used to make prediction. Okay, it's true. 66. Let's see. We arrive at the end. Okay. It's very close, huh, in the score. True or false? The test set should never be used during the training. Okay. Okay. 57. Still, this is the last question. Everything gonna be like here. Let's see. We have George and Lana. Let's see if they're gonna make a comeback or not. True or false? The accuracy metric is often used to evaluate classification model. Come on, you know it. Let's see. Okay, it's true. 57. Let's see for final podium. Let's see. We have third Lana. Okay. Can applaud them. George Vasquez. And funny. Let's see. Did someone make a comeback? No. Okay. Perfect. So again, at the end, give me, I don't know, where is Mohammed, but give me your, where is it? Okay. Give me your name and email, and then I can give you the gift card, which is an Amazon, I told you, small cash, 200 riyal. You can buy whatever you want. Do you think that we should give them also for the podium, Lana and George, a small cash or not? What do you think? Give them? All right. Just come to my here at the end and give me your emails at the end. Okay. Perfect. So before we finish, again, these are my contact address. If you want to collaborate, work on projects, maybe publish papers together, contact me here in my email, and you can see how we can collaborate together. You can note it if you want, or take a picture. And that's it. I hope you enjoy it and learned at least something. And now we're gonna start modeling. So here, before we start, small break, 10 minutes. But I would appreciate if you can give a small feedback here. 2 clicks, 2 seconds. Just scan, put a score and the comment if you want. I really appreciate it. And thank you. We're gonna take 10, 15 minutes. For the contact? Yeah, I will be back. Just let them do feedback they can. All right, I think we can start. Now here, we're gonna try to go through these different steps. Again, the idea here, I'm gonna try to go, again, very fast on all this. This is just to give you an overview. Again, I need you to practice by yourself, layer. This is very important. Now I'm gonna try to go through these different steps just to show you. Of course, you can always practice with me right now, or just follow these different steps. So all the materials are in my GitHub repository. You can find them here. This is my GitHub. You can put a -Halimi as username, and then you're gonna find the repository, Introduction to AI Workshop Series, and you're gonna find all the materials. Of course, go to machine learning layer, and you're gonna find the Jupyter notebooks that you're gonna use. And if you wanna practice right now, I put you here steps to use Ibex. So I don't know if you are familiar with Ibex or not. It's cluster here. So you need to SSH using your cust username to glogin, then git clone the repository, go inside this folder, and ask for a GPU and run this script. Again, just copy paste everything. And you're gonna get a link for Jupyter notebooks that's gonna look like this one. And you're gonna have the folder machine learning. This is for the ones that wanna now practice with me and play with the code. But again, you just need to follow me. I'm gonna show you the all steps, give you an idea, an overview of these different steps, and you can play with it later on your own. You have all the comments inside it, so don't worry. Okay, let's start.
So you should show the GitHub.
Yeah. Just put a-Halimi. And look for users. You're gonna find me. I'm the only one in users. Find it? No? Another ink easy. Go to YouTube. Go to our channel. Found it? For those who doesn't, let me show you. Go to our channel. And here, took videos, I don't know, most popular one, for example. One of these. And here in the description, for example, I put you a link for the GitHub, for those who wanna get the repository. You're gonna find it here. All right? Let me make it full screen. Again, this is how a Jupyter Notebook is gonna look like. And again, you're gonna have all the Jupyter Notebooks here. In your case, you're gonna find Introduction to Machine Learning, 2025. Let me close this. And all the data are gonna be here also in the GitHub repository. Okay, let's try to go through these different steps and see how they look like. So the idea here, again, I'm telling you, is just to give you an overview. I need you to practice by yourself later. Put you a lot of comments on this. And the idea is to go through these different steps. This one, getting the data ready, choosing the right model, train it, evaluate it, improve it, and finally save it, and try to build the final framework, putting all together in a pipeline. This is the idea. So let's start with the first one, which is getting the data ready. For that, we're gonna use what we call CSV file of heart disease. We have seen this in the presentation. We're gonna have some parameters like age, sex, chest pain, etc. And the idea is to predict the target. Does someone have heart disease or not? If we read the data using libraries like Panda here, you're gonna see that it looks like this one, as you can see. It's a data frame, like this one, with the parameters and the target. If you remember, first step to do is to split your data into features and target variable. So for that, we're gonna create our X, which is gonna drop the target and keep only our X, so the features here. And we're gonna create our labels. We're gonna call it Y, which represent if someone's gonna have a heart disease or not, 1 or 0. It's a binary classification here. Okay, now we know how to split this into features and labels. Next step is to split it into training and test. Again, the idea here in the beginning, we're gonna try to get the data ready, go through these different steps. Splitting the data into features and labels first, converting next all the non-numerical features, we have seen this, categorical features, into something that the model can understand, numerical. And finally, we're gonna try to fill all the missing value. This is the 3 steps we're gonna go through. Again, we started by splitting our data into features, labels. Next step is to split this into training and test. For that, scikit-learn make it easy to us and give us a function called train test split, and you can put the size of the test set that you want to do. Here, we're going to take for the test set 20% of our data. You can see that we have 303 samples, as you can see. So if we take 80% for training, it's going to correspond to us to 242, which is nothing, by the way, 200 samples. All right, this is just to illustrate the concepts. Next thing to do when you are working on your own data is to make sure all is numerical, as I said. So we need to convert our categorical features into numerical features. For that, we're going to use another data set here. It's called car sales, and the attributes of this data set, it's make, which represent the brand of the car, maybe Honda, BMW, Toyota, Nissan, color of the car, odometer, doors, and finally, a price. So as you can see here, it's a different problem. It's a regression here. It's not classification anymore. But we don't care. We are looking at getting our data ready, which means doing some cleaning. And as you can see, if we look at the data, it looks like this one. From here, if you look at the type of the data, you can see that this make and color, which represent the color of the car and the brand, are objects, string, not numerical, not like the odometer, doors, price. They are integer. Imagine you want to directly build a model on this without doing anything. So you're going to drop your price to create your features, X, and then Y, right? And you do the train test split. Okay, it's going to work perfectly. But imagine you want to use, I don't know, we will take random forest here. And I want to try to train it on X train, Y train, and try to predict. It's going to give you an error. Couldn't convert string to float. This is why it's important to convert each time the categorical features to numerical. Models, machine learning doesn't like categorical features. We need to convert them into something the model can understand. So for that, let's look at the head before again. You can see that you can take some information about these features, like the brand, make, color, and doors. You can see that we have, for the brand, 4 categories, right? Toyota, Honda, Nissan, and BMW. Colors, 5. White, blue, black, red, green. And doors, 3. So cars with 4 doors, 5 and 3. Now, we're going to use what we call one-hot encoder. It's a function that's going to help us convert these categorical features into numerical features. Now, as you can see here, I put brand, color, but I added also doors. Does it make sense for you? Not really, right? It's a number doors. We have seen this here. In the type, it's integer. Why did put it? Because it's a tricky one. I mean, doors, they are 3 categories. Cars with 4 doors, 3, and 5s. In reality, it's a category. It's not a number like odometer. This is why I told you, like, you need always to look at your data and experiment by yourself and be very careful. It's not just applying. You need to understand your data. Here, doors for me, it's a category. It represents a category, not a number. That's why I added it here as a categorical features. And scikit-learn, again, give us a one-hot encoder, a function that allows me to convert this into numerical thing. But as you can see here, if I put this, this is how it were. It was like this one, and it becomes like this. But why from 4 colon, like make, color, odometer, doors, it becomes 12? The idea behind one-hot encoder is this. If we take here the color column, it's going to be red, green, blue, red, for example, for each sample. The one-hot encoder, what he's going to do is going to take all the category of this column, for example, colors. Here, we have only red, green, blue. And what he's going to do, for sample 0, it's red, right? He's going to create 3 columns, red, green, blue. And he's going to put 1 on the red, 0 on the others. Here, sample 2, green. You're going to put 1 on green, 0 for the others. This is how one-hot encoder is working. This is how we convert in categorical into numerical. And this is why from a data frame that contain only here 4 colon, it becomes 12, because we have seen that make brand here has 4 category, color 5, odometer 1, and doors 3. So the total is going to be 12 here. All right, now we know how to convert our, yeah.
So in theory, a red car is a 100.
A red car is 100, exactly.
And a green car is 010.
Exactly, exactly.
0 and red, 1 and green.
Yeah, exactly. It depends on the categories that you have, exactly. But again, I forget this. This is important. My colleague Didier here, I'm going to help you. Let me just remove this. I forgot to say this. In the GitHub repository, you're going to have this link, Etherpad. just click on it, and you're gonna have wherever you want, put as question. My colleague gonna help on answering that. This is gonna make it very easy for you if you wanna. Just put wherever you want as question, and he's gonna help me answering everything. He's here, so it's okay. Perfect. I forgot to say this. Let's get back. Perfect. All right, we know how to convert our categorical features to numerical one. Here, again, I put everything in this Jupyter notebook, so you're gonna find all the methods that exist. Same thing can be done with another library. Now we have done this with scikit-learn, but you can do it with Panda. Same thing. Here, we have our data frame, and to convert it, you're gonna use panda.getDummies, and you put the columns that you're gonna convert, and it's gonna do the job. But it's gonna do it, and you can see what I was explaining. You're gonna find brand or make here BMW, Honda, Nissan, Toyota, and you're gonna put one on the real samples. But you can see that those didn't work. Why? Because if you look at the type of the data, it's already integer. And Panda doesn't understand that it's categorical. That's why it's skipping it. So we will force it. For that, you're gonna change the type of doors into object and do again get dummies. And now it's gonna work. Doors, category 3, category 4, category 5. Now we have our data numerical. We can split data into training and test with 80% for training, 20 for test, and train our model. Here, I'm choosing random forest, and it's gonna work. Not like before, where we get an error, right? Okay, we know how to convert, we know how to split our data. Next one, what if there were missing values? How are we gonna deal with it? Here, you have two choices. Either to fill them with, if it's a numerical like column or numerical features, with the mean or the average of the column, or to remove them. I don't advise you to remove them because we need the data. Data is very important. So we need to fill them with the average, for example, and if it's a categorical feature, we will add a new category. We call it missing, for example, instead of removing these samples because we need them. All right, now we're gonna use another data set, car sales, but this time with missing data. And if you look at the data, you're gonna see that for each column, this time, we have 50 samples missing, almost. First thing you need to remember, whenever you have missing value for your target variable, which means the labels, which means the column that you wanna predict on, whenever you have some missing values, remove these samples. We don't wanna fake labels. We wanna work with true labels, ground truth. We wanna keep it safe. So whenever you have missing value for your prediction, the column that you wanna predict, the target variable, remove them. Here, as you can see, in the price, we have 15. So we're gonna remove these 15. We wanna keep only true labels. For that, same thing, we're gonna drop here to get our missing, and you're gonna drop all the missing values from the price, only the price, the target variable. Okay, if you look at the length of our samples, before we had 1,000 samples, it becomes 950. It's okay, as long as we don't put some fake labels. It's okay, 950, we lost 50 samples, it's okay. We can deal with it, it's not a big problem. Now, next step is before filling this missing value for the others category, as you can see, we have around 50 here. We need to split our data into training and test before filling it. Why? Because of the data leakage. I told you, We want to keep at all costs the test separate from the training. If you compute statistics like mean or median to do the imputation on the whole data, for example, it means before the splitting, you're going to give your model a peek into the test set. And I told you, want to keep at all costs tests separate from training. So if you take the mean of the column for the whole data, you give the model idea about the test. We don't want this. So each time, before you impute or fill your missing value, split your data into training, test, fill the train with the mean, and then the mean that you get, put it in the test. That way, you don't get any idea about from the test to the training. This is very important. Again, as example, if you compute the mean with the whole data set, the test set information leaks into the training process. This is what you want to avoid. The model may be performing very well, but fail on unseen data. This is why it's very important. So here, we're going to split it as we did before. And now, I'm going to fill the categorical one by adding missing new one. It's category missing. Let me just run it again. Okay. And for the color, it's a category also, categorical feature. I'm going to put a new category called missing, same thing. For the doors, I don't know. We have seen that we have 3, 4, 5. Let's put 4 for the missing one as a category. And finally, the odometer. Here, the idea is to take the column of training of odometer and take the mean and put the missing value as the mean of the column of the odometer. And the result that I get here from X-train mean, I will put it inside the X-test for the missing. That way, I'm not touching the X-test at all. I don't have any idea about it. Yeah. Why? Yeah, because you are taking the mean of all the samples. It means that you have seen the samples from the test. I don't know if you get the idea or not, but to split and then, exactly, we keep it safe. Because if you take the mean of the whole data, it means that you get information from your test if you're going to split it after this. The mean going to be calculated on the whole thing. This is the idea, why we need to separate at all costs each time. All right? Now that we know how to fill all this, again, scikit-learn make it easy using fill NA. We're going to have our training and test filled and imputed, we call this. And we have removed all the missing values. All right? Next step, we have seen this, is to convert these categorical features into numerical. Now that we have filled all the missing values. Same as before. One hot encoder, take these categorical features. Now they are all category, and we haven't anything missed. We can run one hot encoder, and it's going to convert it to numerical things. And we can build our machine learning model here, random forest, for example. Again, I'm giving you all the options. This is, you can do it both with Panda and scikit-learn. Same thing. Each one proposes his own way of doing it. Here, for example, scikit-learn, it's proposing two different functions, simple imputer and column transform. Simple imputer, it's a function, let me run this, that allow me to create strategy. For example, for categorical imputer, I'm going to put a constant and put missing, as before with Panda. For door imputer, you remember we put number 4. And for numerical imputer, I'm going to put the mean as strategy. Here, I'm going to select the features that I want to apply this strategy into it. For categorical features, I'm going to make color. For door features, I'm going to create this and odometer. And now I'm going to apply column transformer, this strategy on it. It's a different way of doing it. It's going to do it at the end of the day. You're going to fill all your missing values. Same thing. I'm giving you all the options. All right, now we know how to convert this and build our machine into working. Perfect. Last step that you're gonna need when doing data wrangling or cleaning is scaling feature. Now, this is an important one. Why? Because imagine you are working, you need feature scaling. Imagine you are working with different scales. For example, many machine learning algorithms are sensitive to scale of features. Why? Because if you take an example, if one feature is measured in thousands, like the odometer as we have seen, another like age on tens, the model gonna maybe give more weight to the large scale features simply because it has a high magnitude, which is not the case. Both are important. Either the age, like you see, from 1 to 20, for example, and the odometer. This is why scaling is very important when you are working with machine learning. You need to scale everything at the same scale. And here you're gonna have two different ways of doing it, either using standard scalar or min-max scaling. So we call this normalization or standardization. Normalization gonna rescale this, all your value between 0 and 1, and standardization is gonna subtract the mean value from all your features. Resulting features have 0 mean. This is the idea. And you're gonna have something between either 0 and 1 or -1, 1. And this is how you can do it. Again, scikit-learn make it easy for us. It gives us min-max scalar or standard scalar. Here, I'm gonna use min-max scalar, and I'm gonna fit transform on my own data, the X-train, and transform it on the X-test. And this is how you can scale all your data between 0 and 1. Now, even the odometer that goes 100K, it becomes between 0 and 1, and everything gonna be easy for the model to understand with the same scale. All right, and you can build then your model and it's gonna work. Perfect. Now we know how to clean our data, right? Next step, how we can choose our model. Here, yeah. Yeah, tell me again. What do you mean by that? Yeah.
What she's asking is like if one feature depends on the other, and then they're scaling, but for training a machine learning model,
Yeah.
one is independent feature.
Exactly, independent features is different.
In that case, in your data cleaning, you have to take that into account and take
Yeah.
them out.
Exactly. Again, Etherpad, ask wherever you want. You're gonna be able to help you. That way we can be very easy on the course is gonna be smooth. Okay. Next one, how you pick your machine learning model to train on, right? Where we were, yeah, we were here. So here, scikit-learn make it easy also, and it gives us what we call a cheat map. If you click here, let me quit this. Not this one. This one. Okay. Here, the library scikit-learn. This is why I'm telling you, always get back to the documentation. It makes it easy for us. It gives us this map, which is very nice. Why? Because it's already tell us for the different problems that we have seen, classification, regression, clustering, dimensionality reduction, which model we're gonna use. How we're gonna do this? Let's see an example. If we take a data set, new one, California housing data set. If you look at the data frame, you're gonna see that it's a regression problem here, right? We wanna predict the target, how much the house will cost, based on these parameters: median income, median house age, average number of rooms, and average number of bedrooms. Now, if you look at the number of samples that you have on this data, you're gonna see it's around 20K, right? how I'm gonna choose my model. I know it's a regression, right? So we start from here. As you can see, start. Do you have more than 50 samples? Yes. Am I predicting a category? No. We are trying to predict a number, right? It's a regression problem. So you go here. Are you trying to predict a quantity? Yes. Do you have less than 100K samples? Yes, we have only 20K. So you go there. Few features should be important. You don't know? Just go here, take ridge regression. Okay, let's try this. So I'm gonna take my data. We have seen this. We're gonna chop the target, build our X and Y, create our training split, test split, and choose the model, which is ridge regression, right? Scikit-learn, again, give us the model. And we can train it on X train, Y train, and we're gonna test it on X test, Y test. How it's gonna perform? It gives me a score of 0.57. Here, the score that it gives me here is the R2 score. What you need to know, one, perfect, and the one, you see, this is the perfect score, one. For the moment, 0.57. I don't like it. It's not okay for me. I don't like the model. So we get back to here, and now we say, it's not working for me. Next model is the ensemble regression. This is, by the way, in machine learning in general, ensemble models are the best. Each time they're gonna perform the best. And ensemble means they're gonna combine a lot of decision trees. We're gonna have random forest, gradient boosting. It depends. This is the ensemble models. These are the best. So here, let's try with random forest this time. He told us from the map to use ensemble regressor, and you're gonna use from here scikit-learn.ensemble random forest. Let's try it, and let's see if we're gonna get a better score than before, which was 0.57. Amazing, 0.8. You see, just by changing a model, we get a better score. Perfect. Now we know how to deal with the regression, right? Problems, how to choose a model, for example. Let's see another example for classification this time. Heart disease. Again, we have our data frame. Look at the number of samples. Here we have only 300. Let's go back. Start from here. More than 50 samples? Yes. Predicting a category this time? Yes. Do you have labeled data? In our case, yes, we have the labels. Here, do you have less than 100K? We have only 300 samples. So yes, we go here, try linear SVC. Support vector machine here. Let me try this with the linear SVC classifier. Amazing, it gives me 0.86. So the accuracy is very high here, 0.86, which is amazing. Now, imagine, without doing anything about the tuning, we are talking about the model by default, without touching anything related to the parameters of the model. And we get very good scores. Now imagine you get a very bad score. Let's see an example, like dummy classifier. You will get 0.52 as accuracy, which means as good as guessing, 50%. Like, is he gonna get heart disease? Yes or no? It's 50%. I'm not satisfied with this. Same strategy, go back to the map, and here, you're gonna say that it's not working. No, go back, and it's gonna send you to the ensemble. I told you, in general, ensembles models are the best in machine learning. I'm gonna use the same model. Random forest can be working for regression or classify. And when I'm gonna use it, let's see how we're gonna perform. 0.86, told you. Each time the ensembles models are in general the best. This is an example of how you can choose a model based on the cheat map provided by scikit-learn. But again, there are a lot of different models that you can play with. And I am asking you always to get back to the documentation. Again, this is very important. So if you get back here, you're going to find all the different models for the different problem that you are working on. Supervised learning, put here, all the models are here. And supervised, all the models are here. So you can play with it as much as you want and get the best model that fits your problems. Okay. Now that we have chosen our model, next step, let me put it in full screen. Next step is to train it, right? We have been doing this from the beginning. We have seen it. So we have our x, y. To train a model, what we are going to do is just call in the function fit. So again, we're going to take our heart disease. As you can see, we're going to take the random forest classifier. We're going to create our x and y features, labels, split into x train, y train, 80% for training, 20 for test, creating our classifier, which is random forest here. And by doing the fit, it's going to train our model on the training. And when you're going to do the classifier score on the test, it's going to predict. So we have been doing this. Again, how the model is going to train, it depends. Each model has its own way of doing it. I told you, maybe it's a linear decision tree. You're going to use some optimization algorithms, like stochastic gradient descent or Adam algorithm. It depends. Each one has its own way of doing it. If you want to learn more about the models, go back to the scikit-learn documentation, and you can see how it's working and how it's training. But here, to train a model, just remember the fit function on the training. Okay, now we have trained our model. Next step is to make some prediction, right? Using this trained model. So for that, we train it using classifier.fit. We're going to use this classifier, and you're going to have what we call two functions, predict and predict probable. If we take our test set and make some prediction using this trained model, it's going to give us these results, 0, 1, 1, 0, which means for these samples, he's predicting if someone's going to have a heart disease or not. 1, he's going to have heart disease. 0, he doesn't have heart disease. Now, how we get these labels? The idea behind this, but before we get how he get it, let's see how we calculate the accuracy. When we do, as before here, classifier.score, he gave us 0.85 accuracy. How we did this? The idea behind this is going to take the prediction here and compare it to the y-true, the true value. Imagine you want to predict on 10 samples. You have the real data, and you're going to compare this to your prediction. If your model is predicting 8 of 10 right, the accuracy is going to be 0.8, right? This is how it's calculating this, by averaging and comparing your prediction with the y-test. This is how you're going to see how your model is performing. You can see that if we predict on x-test and take the mean by comparing our prediction to y-test, it's going to give us 0.85. And if we take the accuracy score for y-test, y-predict, it's going to give us the same score. This is how it's calculating this, the accuracy metric. Now, how we get this 0, 1? In reality, it's just probabilities. Machine learning is probability. So if we take just 5 samples and want to predict on it, in reality, what's going behind this is this. The model is going to give you 0.89. This is the first sample, 0.89. He's confident with the probability of 0.89 that it's 0. And here, this is the probability for 1. So for each samples, if we take the first samples here, it's going to be 0. If you take this one, for this sample, it's going to be 1, because the probability here is 0.51. Same for here. This is how these labels, how the model are predicting these labels. It's just probabilities. Now, why we are taking the labels just by selecting a probability more than 0.5? Because it's more and better than guessing. Guessing is 0.5. So as long as we are better than guessing, we take these labels. You see, we take this prediction for this class. As long as we are better than guessing. This is why here it's predicting 0, here 1, here 1, and here 0, for example, and here 1. All right, as you can see here, 0, 1, 1, 0, 1. We are better than guessing, we take it. Perfect. Here I give, again, I'm giving you all the explanation in comments, so you can get back to it and train by yourself and read this again and again to understand what's going on. All right, perfect. So now we know how to do this for classification. Same thing for regression. If we take the house data set, the model gonna predict on the X-test, but this time it's not accuracy, but it's mean absolute error because it's a number. We are predicting a number, not class. And it's gonna compare the mean absolute error between the y-test and the y-predict. It's gonna calculate this, and the best score here is 0, of course. There is no difference between the value of your test and prediction. All right, perfect. Next step is to evaluate our model, right? Here we have two different functions, score and the most important one, cross-validation score. We're gonna use it a lot. This is very important. So again here, you're gonna see that you can combine it to another parameter is called scoring. Let's see an example. For score, by default, again, you get used to it. Take our X, Y, training, test, split it, train our model, random forest in here. When you're gonna do the score here, classifier.score, by default for classification, it's accuracy. You're gonna take directly accuracy. So here you get the accuracy metric. Now, for regression, the score gonna represent R2 score, not accuracy. But again, best score for R2 score, well, this is what you need to know for the moment. R2 score, the best score that you're gonna get is 1. This is the idea. R2 score, 1, same for accuracy, 100%. And give you the explanation of how your R2 score is calculated here. But by default, just remember, classification is gonna give you accuracy, and regression is gonna give you R2 score. This is what you need to remember. Now, if we wanna evaluate really our model, why I'm saying that the cross-validation is much, much better. Because if you take the same example here, and I'm gonna fit my data, train it, and get a score like 0.85. I'm gonna be happy, right? 85% accuracy. It's good. For me, it's amazing. It's very good. But in reality, when you're gonna use the cross-validation, here you're gonna get 5 scores, not 1 as here. What's going on? In reality, what's going on is here, is this, exactly this. And this is very important. What you are doing from the beginning is taking our data, 100%, for example, patient, and we are splitting 20-80. And we build our model, train it on the 80% and test on the 20%. But is this a good practice? No. Why? The best is to do the cross-validation, to create 5 split. Why? Because here, maybe your model get very good samples here. This is why he's performing very well here on this 20%. So we just lack. But in reality, what you need to do is to split your data, the whole data, into 5 split and test your model by splitting here 20% and 80 here and train it and test it. You're gonna get a score. Do the same thing for the second split, third, fourth, and 5. And you're gonna get 5 scores. You can take the average, the mean, and it's gonna give you the exact how your model is performing on your whole data. This is the exact number of accuracy of how your model is performing on your whole data. It's not just luck like this one. Maybe this is very simple for the model. This is why you get a high score like we have seen, 0.85. Now, if we do this, I told you here as I show you, we get 5 scores, right? And just by taking the mean, it's called cross-validation score. You give him the data, X and Y, and you say CV, which means cross-validation. We put 5, as in the image that I showed you. You're going to split it into 5. And you can calculate the mean of this. And if you compare a single score like 0.85 with the mean of this cross-validation, you're going to see that we get a lower score here, 0.82. But I would rather prefer this one that show me how your model is really performing on the whole data than this one. Maybe you get lucky when splitting the data. So this one is very important. Work always with the cross-validation score. Now, you remember we have been talking on the scoring parameter. For the cross-validation score, you can add the scoring. If we don't say anything about this parameter, it's going to take the default one. Classification, accuracy, regression, R2 score. But you can always play on this scoring. Let's see the different, before we change this scoring, the different metrics for each problem. Classification, we're going to have accuracy. We have seen this. Then you're going to have area under the curve, the rock curve. IUC, we call this. We're going to have confusion matrix and classification report. Let's see these examples. First one, we've been seeing this from the beginning. Classifier.score, give us the accuracy. We have seen this. OK, perfect. Next one, area under the curve, or IUC score. For that, you're going to need to calculate these 4 parameters. True positive means your model going to predict 1 when the truth is 1. False positive, model predict 1 when truth is 0. True negative, 0, 0. And false negative, 0 and 1. And based on these 4 parameters, we're going to calculate what we call FPR and TPR. Again, don't worry. Everything is given us by scikit-learn. It's called rock curve. And based on these parameters, true positive and true negative, it's going to calculate these FPR and TPR. And it's going to allow us to create this graph here. And the score that we are looking for is IUC, area under the curve, this one, as you can see. And here, it gave us a score of 0.93. Again, I'm showing you all the metrics that you're going to find for the problem that you are working on. Accuracy, area under the curve. Here, the perfect score, just to give you an idea, is this one. As you can see, it's 1 when it's like this. Next metric is the confusion matrix. Confusion matrix, if you are working with classification, it's going to give you on how many samples he gets wrong, your model gets wrong, like this one. We are working with heart disease, 0 or 1. So the actual label is 0, 1. And here, as you can see, the model predicted 24 correct, and he got wrong on 5. And here, for the category 1, he got wrong on 4. And same here, 28. This is a different metric that you can use to illustrate how your model is performing for classification, right? So accuracy, IUC, area under the curve, confusion matrix. You can put it like this one, more beautiful, but the most important one that you need to remember and to use each time is the classification report. This is the most important one. Why? Because it's going to give you a very good idea about how your model is performing. Classification report is going to give you the precision, recall, F1 score, which is calculated based on the precision and recall, and finally the accuracy. Now, why is this important, this precision and recall? Because imagine you are working with the data, and you're going to take a small example. You're going to have 10K people, and one of them, only one of them had a disease. You're going to ask to build a model on that to predict this. You're going to build your model and you're going to get 99.99% accuracy. It's amazing, right? You build the perfect model. You are happy. I built the perfect model. No one can beat me. But in reality, what your model is just doing is predicting no one has a disease. In other words, the 10K prediction are false. And you can build this example to show you. If we build this exact example for the 10K and only one has a heart disease, you're going to see that precision for no one has a heart disease is going to be 99.99. So perfect. Accuracy, perfect. But if you look at the precision and recall for the class 1, it's going to be 0. Terrible. This is very bad. This is why you need always to work with classification report. And this can happen in general and most of the time when you are working with data which is unbalanced data. This is why it happens. You have unbalanced data. One category is very high compared to the other one. There you need to remember to look at the precision and recall. Always. All right. Now we know about classification metrics. Regression, same thing. We're going to have some metrics like R2 score, mean absolute error, mean squared error. If we do the fit to calculate the R2 score, same thing. We're going to use, as you can see, the model.score. It's going to give us, by default, the R2 score, 0.8, for example. And mean absolute error, same thing. Scikit-learn give us a function to calculate this between ytest and ypredict to calculate the mean absolute error. And for the mean squared error, same thing. And then you can look at the data that you have predicted, compare it to the actual value, as you can see here. And you're going to get graphs like this one, which gives you an idea about, as you can see in black, the perfect prediction and how your model is performing. We need something for all the samples, something like near the perfect prediction, as you can see. And we're going to have what we call also residual. We need something close to 0 because we are predicting numbers. So we are comparing the prediction with the true value. If it's exactly the same number, the difference is going to be 0. This is what means residual. All right, perfect. We know about different metrics. Now that we know all these metrics alone, we're going to combine it. You remember the cross-validation score with the scoring parameter? Now you can use these scoring parameters as before here, as you can see. Let me just run this here into the cross-validation. We know them. So you can calculate a cross-validation score using a specific one that you like the most. Like here, I like the accuracy. I'm going to calculate it. It's going to give me 5 scores, and I'm going to take the mean. And it's going to give me a very good idea about how my model is working on my whole data. Same thing, you can calculate this for the precision using the scoring method, but this time using cross-validation, which is much, much better. It's not 1 split, 5 split. Same for the recall and for the F1 score. You see, now we have cross-validation with different metrics, which is amazing. You get a very good idea about how your model is performing on the whole data by splitting it into 5. Perfect. Same thing can be done for regression. We're going to have the R2 score from the cross-validation. You put scoring R2 or scoring mean absolute error or scoring mean squared error. I'm not going to run this. It's going to take 5 minutes, so we're going to skip it. But the idea is here. Now that we know all the different metrics for each problem, you can use the cross-validation score, and for the scoring parameters, put the one that you like. Do all of them to get a better idea each time. All right. Next step, now that you have trained evaluate our model is to improve it, how we can do some tuning on our model. Here, it's called hyperparameter tuning, by the way. All right. Each model, if you remember, has his own parameters that you can play with it. If we take the classifier random forest, if we took classifier dot get parameters, these are the parameters of our model, right? You remember how to tune the oven by changing the temperature, cooking time? Same here. We're going to play with these parameters to get a better model. How to tune and improve our model. 3 ways of doing it. First one, by hand. Don't do it. This is just a small example. This is horrible. Don't do it. This is just to show you. Second one, using a function called random search CV. And the third one is using grid search CV. Let's see this. Okay. First thing, you remember the 3 split? We're going to do it. We're going to try to split our data into 70% to train, 15 to tune, which means improving our model, and finally 15 to test. So I have my parameters. I want to work on these parameters. I want to change them, like play with them. Okay, I selected them here. So what I'm going to do, create a function. I'm going to do this. Take my heart disease, do the train split, take 70% for training, validation 15%, and then I'm going to use the X-test, Y-test to test on it. You can see that it doesn't look good, you know? It's exhaustive to do this, manually do the split in here. You see? For me, I don't like it. Better way of doing it, of course, is this. You take your whole data, this one, you split it first, maybe 15% here for test, 85 for training. You forget this. Let's forget it. Put it, I don't know, forget about it. And you're going to take your training, and this time, instead of splitting it only one time, we're going to do the cross-validation, which is going to give us a better score that's going to give us a model that goes through the whole data based on these 5 splits. So again, I'm going to choose one model, train it on split 1, here, 4, 2, 3, 4, 5, train on this, test it on this, gonna get score. Split 2, same thing, gonna get score for full 2. Same model, again, split 3, gonna get score. So at the end, for the same model, I'm gonna get 5 score, gonna calculate the average. It's gonna give me a score that represents this model, an average on the whole data. Then I can change the parameters of this model, do it again, and I will see how model is performing better on the training based on the average score obtained based on the cross-validation. This is the better way of doing it. And then you can test your best model that works very well on the training on your test data. So let's see how to do this. Again, we have our X, Y. We're going to take 15% for test, and X train, Y train, 85%. Now, quick remark here. When you are doing the splitting, add always this stratified. Why? It means, this is an example of how you can split your data, for example, into 15% for test and 85% for training. Why we add the stratified split? Because imagine you give your model all the samples and randomly you split your data. Maybe when you're going to split your data, you're going to take all the samples from category 1 and nothing from category 2. We don't want this. We want to build a model that classify the 2 classes. So for that, what we want to need is to split the 85 from here. So it's going to give me this. And 85 from here. I want to be sure that my model take 85% from both classes. Not randomly, and maybe you're going to take all the samples from one class and few for the others. This is why stratified is very important. Always use it. Okay, now we split our data into training test. Test, we're going to forget it. Next thing, to take this training, and now that I take this training, I'm going to do the cross-validation on this training into 5, split, as you can see here. And if you look at this, let me try to run this. I'm going to use the cross-validation score as before, but this time on the X train, Y train with 5. I'm going to take the mean. Perfect. We have our, what we call baseline matrix. So why I'm saying it's baseline matrix, because I took the random forest classifier with his own parameters by default. It didn't touch anything. Okay, we have our baseline matrix. So as you can see, it's going to give me on the training the cross-validation scores. And the mean, this is what we are looking for, 0.8134. Let's see how we can improve this. And these are the metrics on the test. All right, we have a baseline that we're going to need to improve and to compare it. Again, another advice. When you are working on this kind of stuff, try always to maximize this, the mean cross-validation on training, not looking at the test and try to maximize this. I know, it looks like it's very good, like I got a better model with a better score on the test. No, try always to maximize and get the best scores on the training using the mean cross-validation score. Not on the test, because I've said in the test, you don't know what samples do you have. Maybe it's an easy sample. So if you are very happy and get a very robust model that works on the training, you don't care about the test. Maybe it's going to be hard. Maybe it's going to be easy. But at least you know and you can convince people that you get the best model that works on your training the whole day, on your whole day. This is the best that you can get. Then how it performs on test, it differs. But at least you are sure that this is the best for your whole training data. All right, now again, we have our baseline model. Let's create the first try to improve it. First method, by hand. Don't do it, but just to show you. I'm just changing the number of estimator. I'm putting 200. Let's see. Okay, amazing. You see, just by changing the number of estimator to 200 for the random forest, I got 0.82, a better score than the default one. And for the test, it turns out that performed very well. Okay, it's good for me, I like it, but this is the most important. On the training, I was able to improve it, okay? Sorry, I don't hear you very well. Don't know if you can get them. Yeah, just try to get it. Yeah. Which number? The 200. I'm telling you, it's by hand. I do it randomly. No, this is what I'm trying to explain. Don't do this. This is terrible. Don't work with hand parameters. You are choosing the one. Don't do it. I'm going to show you just before this the right way of doing it. This is just a small example to show you that I'm changing the parameter by my hand and it appears that I get a better model. But this is a terrible thing to do. The best way to do it is to use functions like random search CV, for example. This is the right way of doing it. Now, if you are talking about how you can choose this dictionary, this is different question. This is, you need to get back to the documentation and see which parameters works best with which model. And by experience, I've been working on that a lot. I know that these parameters are gonna give me a good model. But again, everything is on the documentation. You need to get back into it. But this is the right way of doing it. Yeah, Brenda? Yeah. Yeah, it depends on the models that you are working on. No.
No. This is something that is hard to already the algorithm. You are going to a range of different numbers on each parameter. Here is exemplifying something called an estimator that is very pertinent to just random forest. There are other models that have other things, like for example, the so-called.
Yeah, it depends on the model. If you look at the random forest, as you can see, yeah. No. With the algorithm, we are working on the model to try to get the best parameters using this model, for example. Here, it turns out that I choose random forest, and these are the different parameters, as you can see, when you do get parameters. And I'm playing with this, giving it some range. So, the right way of doing it, don't use the one by hand. Use random search CV. So you're gonna give him a dictionary with the parameters that you wanna change and play with some range. So an estimator go from 100 to 1,200, for example. And if you look at to this, the idea behind this, if you take this number, so for an estimator we can find 5, max depth we're gonna choose 4 to test, max feature 2, 3, 3. If you multiply this, you're gonna see that it's equal to testing 360 models. Now, it's a lot. Random search CV, what he's gonna do is he's gonna choose randomly between these parameters based on a parameter that you're gonna choose, which is called an iter, which represent how many model or variant you wanna test. I don't know, here for example, I wanna test only 20 model. So between these 360 models combination, you're gonna choose 20 models and test them. Using, again, I'm not gonna run this, it's gonna take a while, but just to show you, using random search CV, the cross validation. So it's amazing. What he's gonna do for me, I'm just gonna tell him, these are the parameters that you're gonna work on, choose 20 models and do the cross validation on it, and give me the best model from it. And what you're gonna do is taking this, fit in these 20 candidates 5 times, and calculate the average, and it's gonna give me a score, the average score for these 20 models, and you're gonna choose the best between them and give me the final best model, which is amazing. So here, 5 multiplied by 20, you're gonna do 100 fits, which means 100 train. And at the end, you're gonna give me the best model with the best parameters that he found. And it turns out, if you look at the score, it's 0.8249. Amazing, we improve it. Okay, and on the test, we are around 93 accuracy. Perfect, random search CV works very well here. We get the best model based on the dictionary that I gave him. Now the next method, and the last one, is the grid search CV. Imagine you don't wanna do random search CV. You don't wanna choose only 20. You wanna do an exhaustive thing through the whole parameters that you have selected. If you take before, it's 360 models to test. It's a lot. Here it will depend on the resources that you are working on. I don't know, you are using IBEX or cluster, you can do it. But again, random search CV in general gonna give you a good model. But if you wanna be sure that you want the best model, you do an exhaustive thing grid search CV, and you're gonna test all the models. Now here, again, 360, it's a lot. So I reduced some parameters in order to get only 72 models to test. And I'm gonna do grid search CV this time with, again, 5 folds as before. And let's see how it's gonna perform with the random search CV. Okay, the grid search CV gives me the best parameters, and we get almost similar to before, 0.8288. Same for the accuracy. So again, it's gonna take a while, by the way, if you're gonna do this. So in general, random search CV is more than enough. And if we compare our model performance, you can see that the baseline was here for the accuracy, precision, recall, F1 score. By hand, we get a better score, but don't do it. Again, this is just to show you. I don't know how I was able to get a better score, by the way. Random search CV, on the other hand, we got a very good score, as you can see, for the precision, recall, and F1 score. And we got better than grid search CV. Again, grid search CV are reduced the amount of parameters. It's not the same as random search CV. But I told you, in general, random search CV is more than enough. But now that we know all this, we have been using what we call random forest. But you can take it a step further and use advanced model, which is called gradient boost decision trees, GBDT. For that, you're going to use XGBoost, CatBoost, like GBM. These are advanced models. And in general, you're going to get better score and better model. And you're going to do the same thing, for example, but this time, instead, so we're going to put our dictionary for XGBoost here, same as random forest. We're going to build our classifier, XGBoost classifier. And we're going to use, instead of random search CV and grid search CV, we're going to use what we call Bayes search CV. It's a Bayesian model, an advanced model, which means he's going to try to converge to the best model quickly. So I'm going to give him only some iterations, so 100 here. So you're going to test for me 100 model based on this dictionary, which is a lot. But I know that this is an advanced model. Bayesian is going to use some distributions like posteriori, prior. It's an advanced thing in order to converge to the right parameters faster. And based on that, for the XGBoost, let's see how it's going to perform. Amazing. We improve it, always talking about the cross-validation mean score for the training into 0.84. Yeah. Yeah, no, a model, very known model. Is the model, exactly. Bayesian search is similar to random search CV, but it converges. Random search CV is going to take randomly these parameters. Bayesian search CV is different. It's going to look at to the optimization and look at for the best parameters quickly. It's going to converge to the best model. It's an advanced method, but it's working very, very well with XGBoost, and you can apply it with random forest also, this method, with any model. And you can see that we were able to improve our model to 0.84. Amazing. And these are the scores for the test. So we are trying to improve this. Don't forget. CatBoost, similar thing. It's another model. We have random forest, XGBoost. This one is another one, CatBoost. And you're going to use the same thing using Bayesian search CV. I'm going to tell him, look at to 100 different models and give me the best one. And at the end, 0.8484. Amazing, better than random forest. Last one, light GBM. I'm going to give him the dictionary. And same thing, look at to the best model using 100 variants between these parameters. And we get 0.85. Told you, it's an advanced models. These are the best for the machine learning. And then you can compare all your models and the techniques that you have been working on. But again, this is the cross-validated mean scores based on the different methods that you have used. The baseline is here, 0.81. The hand model, I don't know how we get the 0.82, but we get it. Then we have the random search CV, 0.82 also, and we improve it into light GBM, which is 0.85. But if you look at to the test, you're gonna see that on the test, it's performing a bit similar between random search CV, light GBM, XGBoost on the test, as you can see here. We get the same, 0.96. But again, I told you, the test is good. Okay, you can confirm that your model is doing very good. But what we are looking for is this. Try to maximize this. This is the most important. This is why light GBM here in our case is the best one to choose, because he's worked very, very well on our whole data. Even it's performed similar to random search CV on the test. But we don't care, because I'm sure that my model is the best on different kind of scenarios. We're gonna work very, very well on different kind of scenarios. This is the idea. Perfect. Now you can save your model using different methods like pickle and load it again and predict. Don't know if it's gonna be loaded here. Okay, you see, I already trained my model and just load it and predict, and it gives me the same scores as before for XGBoost. Different way of doing it, JobLeap, another library that you can use. Same thing, I can load it. Okay, it didn't work here because it needs the function. And I can test with it again. Why is it important to save your model? Imagine you are working for big data. Don't have time. Resources cost a lot of money. You're gonna train your model, save it, maybe train it again. So you load it again and train it on new data. Maybe you received new data, you wanna train on it. Always save your model, train again, and save it and predict on new data, for example. Each time save your model, don't forget to do this. And finally, now we can create our pipeline. It's a function that's gonna allow us to group all these steps that you have seen from the beginning. If we take the missing value of the car sales, same, we have seen this. We're gonna create what we call a function here provided by Scikit-learn, also pipeline, which is gonna make it easy for us. It's just a function like a framework where you can combine all the different steps that you have seen. So data wrangling, data cleaning, all this, training, everything, into one pipeline where you can build your preprocessor who's gonna do all the steps that you have seen before, filling the missing value, converting the autoencoding, scaling, all this. We're gonna put it into what we call preprocessor. And then we're gonna choose a model. And you're gonna call it and put it inside a pipeline. And then it's gonna be easy for us to call this pipeline again and to work with it. If we take, for example, this X and Y, we split it, and we're gonna use this model to fit it. It's gonna already do the data cleaning and the training because it's inside the pipeline now, just to make it easy for us. Now that we have this pipeline ready for us, next step is to test different models. Okay, I have a problem. I already created my pipeline that's gonna do the data cleaning and the training and the prediction. I wanna test a lot of different models. Okay, I will create a dictionary, regression models here, for example, because I'm working on a regression problem. And I'm gonna create and test ridge regression, Bayesian, Lasser, XGBoost, random forest, light GBM, CatBoost. Create this dictionary, and I will launch from it using my pipeline, because I know that it's gonna do the data cleaning and choose a model. So I'm gonna do a loop on this different dictionary and test different models. And it's gonna give me the average cross-validation scores for each one. Amazing. Now you have an idea directly about how each model is going to perform on your own data using this pipeline. Now imagine, to go further, I like CatBoost and XGBoost. Let's take it further. Now that I like these two, I have an idea and I like them, I'm going to add what we already seen, another dictionary for the parameters, and launch again this pipeline, which is the model here, on grid search CV on these parameters to get again the best model using different parameters. So I have an idea, a quick idea about how each model gonna work on this, my own data. I select two of them. I like CatBoost, the result of CatBoost and XGBoost, and I want the best model using the best parameters for this CatBoost and for this XGBoost. So here you can do the grid search CV. We have seen this, and it's going to give you this. So you have the preprocessor, the CatBoost, and it's going to give you the final best model for CatBoost on my own data. I'm going to do the same for XGBoost. So I'm going to give him some parameters, grid search CV to go through it, and it's going to give me the best model for XGBoost. Now the final step, and I will finish, to take it a little bit further again and get the ultimate model, I'm going to take these two best models and combine them into one using methods like stacking and voting regressor. And here, as you can see, this pipeline, like voting regressor, is going to take my model, the best one, go all the preprocessor, learning everything, and combine it with model second model. And it's going to give me two scores because I'm using two methods, stacking or voting. And we take it a little bit further and get the final ultimate model. As you can see here, it's stacking model here. And this is the final scores and how you can get the ultimate model at the end. And that's it all of today. Again, I'm telling you, this is just an overview of the different steps. You need to get back to it by yourself and to practice by yourself. Put you a lot of comments, just clone the GitHub repository and work by yourself. And that's it. Thank you all. Thank you. Thank you. All right.